So we're gonna go over the normal force, and this is just simply a simple thing. So the normal force is honestly, when you read physics textbooks, they'll typically just extrapolate things and nuance things, but most of the things are the same concept. Like weight and Newton's second law are the exact same thing. So, or weight and force is the same thing. So the normal force is the perpendicular force a surface exerts on an object. So this is literally like the simplest thing ever. I mean, um, let's say that we're standing on the ground. And also, the ground technically isn't flat. I mean, it's a circle. So, I'm not sure if you can find a perpendicular. Actually, yeah, I guess there's a tangent line. Okay, so, I mean, let's just say that you're standing on an infinitely long line. Or you're just standing on the floor. We'll just assume that the floor is a line, a perfect line. And I'm standing here. The force I'm exerting onto the ground is called the normal force. It's perpendicular because you notice that the ground is this way and my force is being exerted onto the ground this way. So if I'm pushing an object like this technically isn't a normal force, Fn, which that's what it's denoted as. But if I push down on this force here, that means the force is going downwards while the object is this way, and that is what a normal force is. So this is just more extrapolation. If you press down, the surface pushes back up. I mean, that's pretty self-explanatory. Again, Newton's third law. It's simple logic. Any force gets exerted back on you, so I don't know why they really mention it, but probably just deduce. I mean, I don't know. So if I am standing on this, the force I'm exerted, which is actually force equals mg, ma, um, g m1 over m2 divided by r squared. I'm just saying this because all these formulas are the same exact thing. The force I'm exerting onto the ground, it's exerting the same force. That's all that means. And this is a little bit more complicated. So if you have a completely flat surface with object, the force you're exerting would be mass times gravity, as we know. So would be mass times gravity or mass times acceleration. Same exact thing. So the force I'm exerting here is just ma. Or mg, same thing because acceleration is gravity. But if you do an extra downwards push, so let's say there's a let's say there's like a hydraulic press that's pushing down on this guy's head. Then the force would be the hydraulic press, which is mass times acceleration, and also the person's downward force because of the gravitational pull. So it's mg plus ma equals Fn, which is quite self-explanatory because that's the amount of force we're putting on this perpendicular surface. You can also write this as Fn minus ma equals mg. Wait, is that right? Yes, yeah, that should be right using your simple algebra. Fn minus ma equals mg. I'm trying to understand this right now. Okay. Yeah. So the force minus the because this would be a net force or net vector of ma plus mg. So again, the normal force is just the total force you're exerting on this perpendicular surface here, which is just net force. So then to find the force of mass times gravity, you would just do Fn minus ma. Pretty simple stuff. Yeah. If you pulled it, it would be W minus F up. So remember W is just weight, which is just mass times gravity. So let's just assume this perpendicular force exists again. Let's not use a hydraulic press. Let's use a crane here. And let's say this crane is clamping down on this person's head and pulling him up. That means the force that is being exerted here, since this is slowing down the acceleration, these would be vectors pointing in the opposite direction. So, I mean, I guess it would still be force equals ma plus mg, but technically, mg is pointing in the opposite direction because we're taking the force off the perpendicular object. So the normal force is being exerted. So we can write this as ma minus mg, minus the magnitude of mg, but it's still the exact same thing. You're just taking off the force, and F plus mg, or not mg, I guess it would be negative ma. F plus negative plus. And force minus mass times acceleration, or force plus mass times acceleration, will equals the mass times gravity, because the net force, or the normal force, will be how much force we're exerting on this object. So that plus this mass times acceleration would equal mass times gravity, because sorry, I'm thinking. Because the mass times acceleration in this net direction is negative, so we're just subtracting the normal force, and then we're subtracting a negative, which becomes positive a. So I guess we'll do absolute value. So F of n plus mass times acceleration equals mass times gravity, because the normal force plus the mass times acceleration. Wait, should we absolute value? No, it would be Fn minus ma, I guess. Wait, no, I mean, it's kind of hard to say because mass times acceleration here would be negative. So let me explain this again. So let's say here, and let's say we're coming down here with a force of ma. So that means right now the force net is ma. So that means let's introduce, or sorry, not the net force. I mean, yeah, the net force, but I would say the normal force because that's what we're learning about. And let's say a force right here is taking, let's just say a crane, again, is clamped onto this guy's head and pulling him up. And let's say this has a force of, sorry, this would be mg. I mean, it's the same exact thing because g is just a in this case. And let's say this is mass times acceleration acting upwards. So that means this is taking the force off this perpendicular object. So that would mean F net equals mg plus ma, or minus ma, minus the magnitude of ma. Because the force of this object, let's just say if this is taking 5 newtons off and you're pushing 10 newtons into the earth, since we're pulling 5 newtons off, which means that this is a vector force of 5 newtons this way, 10 newtons that way, if we use simple tail-to-head or head-to-tail addition, the 5 newtons will clamp on to here and go back 5 newtons. So simply we're relieving 5 newtons of force, we're pulling 5 newtons of force off, which is why it's F equals mg minus ma. But it could technically be plus ma because this would be a negative vector, but again, it depends on sign convention, and here I'm sure they're using magnitude. So in simple terms, we're applying 10 newtons of force here with our weight, and we're pulling 5 newtons up with the clamp, which is why it's a net. If we do the math here, it would be 10 newtons minus 5 newtons technically, because this is magnitude, and we'll get 5 newtons of force that we're applying onto this object. So that's the logic here. So if you pulled it, it would be W minus F up. Same thing here. Remember, W is just mg. So apparent weight is the scale reading which equals the normal force. The formula is F of n equals mg plus ma. At rest, F of n equals mg because you're not putting... So think of it as like an elevator. And let's say this is elevator here. If we did nothing and we just cut this elevator's rope, that means the force would be ma, or mg, same thing. So let's say a person is here, they're exerting a force of mg downwards. And this whole elevator is exerting a force of mg onto the ground. But if we slow down the force by pulling it upwards, then that's another vector, which will minus ma, because we'll take another force and we're going to push this elevator upwards. So when an elevator is going up floors, you're subtracting a force that fights against the gravity's force, pretty much. When you're pulling it down, you might add force to make it go a little bit faster than gravity. But I guess gravity is quite quick, so there wouldn't not be too much point of that, but you would add a downwards force of ma, and you would subtract the force of ma if you were trying to slow the fall. So that's the logic here between the normal force. Quite a lot of things, but it's just the force that something exerts on a flat surface. That's it.